next talk with Gabriele.
Hello, hi.
Hello. So Gabriele will tell us about correlated bath and heat engines. Thank you.
Okay. Everything okay with the video? Audio is fine? Yeah.
Yes.
Yeah, okay. So good morning, everyone. First of all, let me thank Camille, Ilya, and Francesco for organizing this meeting. I mean, it's great that even though I would have loved to go to South Africa for the first time, it's still nice to have these activities online. Okay, so today I'm going to talk about quantum thermal machines powered by correlated baths. First, a little bit of background and motivations. Perhaps this is not so necessary here to motivate the study of open quantum systems for applications in transport, complex systems, quantum technologies, and quantum thermodynamics. Now, the usual approach that people do is to consider microscopic models, very common ones like Caldera-Leggett, spin boson, or more exotic like spin star networks or even fermionic paths for metallic systems, and then to do a series of approximations because the problem would be otherwise too complicated, like Bode-Markov approximation, and then end up with a Lindblad master equation. This is all good. This is all very well established, but problems arise when the system that you want to describe is made of several small parts, like subsystems, where, for example, S1, a part of it is coupled to a cold environment, E1, and another part, like Sn, is coupled to an environment, for example, at a hot temperature. And now there are, say, the correct approach would be to use the so-called global master equation, which say the textbook approach, which is to say you need to find all the energy eigenstates of the complete system and then write the jump operators for each of the units coupled to the environments and in order to write the master equation. So even writing the master equation, leave alone the solving the master equation, is computationally hard. So a very common approach is actually to say, okay, if the interactions between the subsystems is not so strong, one can just say, well, I'm going to write the master equation for S1 coupled to the environment. I'm going to write the master equation of Sn coupled to the environment, and then I'm going to put all together and write a complete master equation for the whole system with local jump operators on S1 and Sn. This is what we call the local master equation approach, and this is very, very common in the literature. Maybe it's not being called like that, but it's, say, the standard in quantum optomechanics or dissipative optical lattices, harmonic chains, spin chains, tensor networks like matrix Floer states with dissipation, and even quantum engines. There are many, many examples of this approach. The problem is that not always local master equation can describe faithfully a physical, say, a physical reality. And there have been a lot of comparisons of local versus global. There is not much consensus, especially when the system is driven. When the system is not driven, it's clear that the global master equation is the correct approach if the secular approximation can be fulfilled. But there was a very, I don't know, seminal paper, very distinctive paper by Levy and Kozlov that showed that the local approach to quantum transport may violate the second law of thermodynamics. And they actually consider a very, very simple example of two harmonic oscillators coupled to two baths, one cold and one hot, and they show that sometimes it's possible to find heat spontaneously flowing from the cold to the hot baths. And what they found, in fact, was that the current from 1 to 2 is not proportional to the temperature gradient, as you would expect, but is proportional to the thermal occupations in the two baths, where this is the usual Bose-Einstein distribution in the two baths. And therefore, the sign of the current depends on the sign of the ratios of temperatures to frequencies. And therefore, if we change the frequency, we can change the sign of a current. Sorry, I'm making a little bit of mess with Zoom. Okay, and so therefore, the local master equation sometimes predicts spontaneous cold to hot current, so which is quite unusual. And okay, sorry again. So let's see what's wrong with local master equation. So local master equations are in Lindblad form, and therefore they are completely positive, okay, and trace preserving maps, and therefore they must correspond to a microscopic quantum model. And one possibility is to use collisional models, which we have heard already during this conference. They're also called repeated interaction models, where the model for the environment is slightly different than the usual one. The system is coupled alternatively to a series of units from the environment, ancillas, for example, that interact with the system and then they fly away. They interact for a very short time with the system and then they fly away. And they usually, or say, the simplest case is that they are prepared in an initial thermal state. And now, so part of this talk, I'm going to show you that thermodynamic laws are observed, provided that all energy and entropy contributions are taken into account. In particular, the heat current from the baths number I can be simply calculated as the energy change of the ancilla before and after the collision, divided by the interaction time tau. And the new thing is that, in principle, there is also a work term, because the total Hamiltonian system plus environment is time dependent, because you have to switch on and off the interaction between system and the environment units. And this time dependence of the Hamiltonian may lead, not always, but sometimes may lead to an external work given by this integral. In some cases, these two expressions can be calculated very easily. So the conclusion for this part is that it's actually this work here that is responsible for the cold to hot current. So local master equations in cases like this do not correspond to a situation where the environment is static, but to a situation which is dynamic, and there is a time-dependent Hamiltonian in the system-environment interaction. And the second conclusion, which is a little bit more provocative, is that any CPT map is actually compatible with thermodynamics, if provided that everyone does the microscopic analysis of energy and entropy balance. Okay, so let's go to the second part of today's talk, which is an extension of this method, where we consider correlated ancillas. And we consider a system which is similar to the one I showed before, where there are a series of ancillas created at cold temperature T1 and another set of ancillas created at temperature T2. And they are at this strange angle because the idea is that we then correlated them with a unitary operation. And after that, the emerging ancillas, which are now this green, means that they are correlated. They locally interact with each part of the system, S1 and S2. So first of all, I'm going to define resources for this case. So we're going to see two scenarios for this. And the second question that I'm going to address is the effects of quantum or classical correlations in the heat transport and performance of thermal machines made with these correlated environments. So first of all, let me talk about the definition of resources. So the first scenario I'm going to describe is so-called partial scenario, where, say, if you want, this is enclosed in this rectangle here, and this excludes the unitary operation U between the two ancillas. And that means that we treat the correlated ancillas as a free resource. They are given to you, and we don't pay for them. And this means that actually this can violate thermodynamic laws because, in fact, the ancillas are not overall in a thermal state, and they are not always in a local thermal state. The second scenario, instead, we call it the complete scenario, and we take into account everything. So from the preparation of the ancillas with the unitary U. The only thing we don't take into account is the thermal baths, because these are, as usual in resource theory of quantum thermodynamics, thermal baths are free. So it includes the unitary U, takes into account the cost to correlate ancillas, and therefore this is always going to be consistent with thermodynamic laws. The first case that we consider very simple, just to start, was you assume to be a partial swap with parameter phi. And the effect of the partial swap, as you can imagine, is to swap the populations of the ancillas. So if N1 and N2 are the populations of the ancillas after the collision, you can see one initially was for phi equal to 0, one was at 1 and one was at 3. And as phi grows, the populations are swapped. And eventually they are completely swapped when phi is equal to pi half. So phi equals to pi half corresponds to the complete swap, to the total swap. So let's see what happens in the partial scenario. So in this plot, I'm plotting the work and the heat currents Q1 and Q2 from the two baths. So as a function of phi, of the swapping angle phi. So when phi is small, this situation corresponds to an engine. So here I have to look at the work. The work is negative, so that means that this is work that is produced. And when phi is above pi over 4, everything changes sign. So all the currents change sign and the work becomes positive, which means this is actually injected into the system. And the heat Q1 also becomes positive, which means heat is extracted from the cold baths. So that corresponds to a refrigerator. And as you can guess, the crossing point between the engine and the refrigerator point, these are Carnot points. This is all periodic and repeated from pi half to pi, and so on and so forth. So this is it's just a periodic situation. So this is the partial scenario. And we can see that we can optimize. So first of all, we can switch operating regime of the machine going from the engine to the refrigerator. And the second thing is that we can maximize the operation of the refrigerator by going to the total swap. In the complete scenario, instead, what we see is that there is no sign change. This all remains in the engine regime. The difference is that for phi equal to 0, you see that there is very, very little heat currents and work produced. And when phi goes to pi over 2 to the total swap, then this is all amplified by actually 10 times. So the maximum performance, the maximum power that you get is for a complete swap. And this is reminiscent of a paper by Campisi, Pecora, and Fazio. And we also analyzed very recently the engine with swap operations in this paper here with Piccione and Bellomo. Okay, so this was for a simple case of partially swapped ancilla. I'm going to move to a rather more complicated case, which is the random unitaries, and where U is taken as a random unitary with a uniform distribution. And now you're going to see a fancy histogram of the work and the heat for all these unitary operations. I think this is something like 10 million unitaries. You see the distribution is broad, but is limited by extremal points, 8 extremal points 1 to 8, that form a nice octagon. And these extremal points 1 to 8 corresponds to non-correlating transformations. So these are transformations that if your density matrix of the ancillas is initially diagonal, it leaves it diagonal. In particular, 1 here is the identity, and 2 here is the complete swap. And these are all combination of these local flipping, etc., etc. So you can see the distribution is limited by this non-regular octagon. And then this line here, okay, maybe let me put this, the engine, just to tell you, corresponds to negative work. What you get above is a mixture of accelerator and in few cases a refrigerator. So the engine, which is what we are interested in, is in this shaded area. And the best points that creates the smallest possible value of the work, so largest in absolute value, is again the total swap 2, which is again extremal in this plot. We then looked at correlations and the relationship with work and heat current. And so here we looked at the mutual information between system and ancilla after the collision. Again, you can see the histogram as a function of the work, and here the mutual information in the vertical axis. Here are the 8 extremal points, extremal operations, which now they are not extremal anymore. And this is the reason is that the mutual information is not a linear function of the operation anymore. And something I wanted to notice, again, this is the engine. So identity is here. Total swap is the one with the largest value of the work, and actually smallest value of the system ancilla, system environment correlation. But what I want to stress here is that you need this non-zero correlation in order for the engine to sustain the functioning. And then we looked at the mutual information at steady state between the system and the system, so S1 and S2. Again, a broad distribution. This is the engine operating regime, and the total swap is here. It's actually quite a large correlation between S1 and S2, and that means that we need these correlations for sustaining the functioning of the engine. So this is the morale. We need these system bus and system-system correlations, not necessarily quantum correlations, for the thermal machines to continue working. Okay, and that's my summary. So I've told you very briefly about local master equations and their consistency with thermodynamics. This can be demonstrated with collisional models that we did in a paper a couple of years ago. This can also be done without invoking collisional models and using just non-commutativity in quantum theory. And if you have missed Alberto's talk, go back and check on it. And then the second part was about an extension of this to a situation where the bus are correlated. And I showed you that classical correlated ancillas are extremal, the total swap is optimal, and that you need these correlations for in the steady state for the machine to continue working. I'm going to advertise also a new work that we have just finished on the following, that any Lindblad master equation, local or global, in fact multipartite, can be efficiently quantum simulated in quantum computers. And this is in collaboration with Roberta Zambrini's group, and I advertise Marco's talk on Thursday. And with this, I just thank my collaborators and you for your attention.
Thank you very much for the very nice talk. Let me check if there are questions. Let's wait a bit. Okay, Sebastian Defner says, very intriguing results. Have you looked at Discord? I mostly wonder whether quantum correlation still would give you any distinct quantum advantage. Yeah. I mean, this is a very interesting question. So we looked at Discord, and if you're interested, go check in the paper. There is not much more that we learn from Discord that is not already in the mutual information. So for say the quantum advantage point, there is not much that we can say here. We don't clearly see a quantum advantage there. It seems that classical correlations between the systems will be equally valid in this point. I think that the reason for this is that all these interactions are local. If you had a model where you could make the two ancillas interact with a global, say, 4-point or 4-body interaction between system and environment, then I would really believe that, for example, you could even use entanglement as a mean to increase the power of the engine. I believe that because these interactions are local, we kind of do not exploit all the quantum correlations. I think even classical correlations will be fine. And again, this is the reason why these classical non-correlating transformations are extremal. Okay, thank you very much. That was very clear. I don't see more questions. And since we are a bit late on schedule, we'll close the session. Thanking again all speakers. And